Hello, Yuma. This time we are going into indirect proof and some triangle inequalities. We're actually covering three sections that I think warrant being covered in one day. Okay, there's some stuff that I want you to see, but we're not going to do a whole lot with it. But I do want you to be familiar with the vocab and know what we're talking about. So we'll go through a couple things, and then the last couple sections are fairly straightforward, I think, and we'll get you going on them that way. So in order to try and keep it under 20 minutes, we'll get going kind of quick here. All right, so we're going to use indirect reasoning to write proofs, use inequalities involving angles and sides of triangles, and then apply those inequalities to two triangles as well. Okay, so indirect proof. All right, so this is a kind of little game that we enjoy. Here's the goal. To fill in the empty squares in each of these rows and columns, we got to have a 1, 2, and a 3, and a 4. They must appear once and only once in each row and column. So how do we go about doing something like this? Well, my first cue, I look right at this section right here, that little box, and I see that that can't be a 1, or else I'd have 2 of those in one row. Can't be a 4, can't be a 2, therefore must be a 3. Following that logic along, I see that this can't be 1 or 3 or 4, must be a 2. What do I have here? Okay, this can't be 1, 2, 4, must be 3, means this must be 4. All right, so you see how it works. That's got to be a 3, 2, 1, 4, 1, and 3. All right. And by the way, I just included another one just for your fun. If you want to go ahead and do that, copy it down and do it on your own. Anyway, what we've just done is use something called indirect reasoning. We didn't use a logical sequence of things we knew, but instead we considered the possibilities and then eliminated the ones that had to be impossible. So this way we arrived at conclusions that were the only ones left, therefore they had to be true. So this is called, if we use a proof to use this kind of logic, we call it an indirect proof, all right? So often, for the case of an indirect proof, what we're going to do is we know there's only two possibilities, either it's true or a false, okay? And then when you see that one of these possibilities leads to a conclusion that contradicts something you know it must be false. And for this reason, it's sometimes called proof by contradiction. Let me tell you what we're going to do with them. To write an indirect proof, the first thing is we're going to make a temporary assumption that what we want to prove, well, let's say it's false. And then, as we follow our logic through, we find out that if this assumption leads to something that's impossible, well, that assumption can't be true. Therefore, what we wanted to prove must be true. Let me give you a specific example here. All right, so we've got a triangle ABC, and what we know is that BC is greater than AC. That's a given. So BC is longer than AC. Longer than the other one. All right, you got it here. BC is longer than AC. So to do an indirect proof, if we want to prove that angle A is not congruent to angle B, all right, so we're trying to prove that this is not the same as this. Well, so what we're going to do an indirect proof is assume they are the same. Assume that those two angles are going to be congruent. Well, then we follow our logic. If they are congruent, then by the converse of the isosceles triangle theorem, then BC would have to be congruent to A. If these two angles were the same, the isosceles triangle theorem tells us that these two side lengths must be the same. But that contradicts our given that says that they're not the same. Therefore, those two angles not being congruent, that's the only logical conclusion. All right? So we assume that the opposite of what we want to prove is true. We follow our logic until we find that something goes wrong. Therefore, we know what we needed to prove was in fact true. And here is one to try on your own. You can pause it, give it a try, and then I'll reveal the answer. All right, here we go. And you can read along with that. See what we did. We assumed that the angle was a right angle to contradict our proof statement there. And when we did that, we ended up finding out it couldn't be true. Therefore, what we wanted to prove had to be true. Moving on, Inequalities in one triangle. All right, going back to chapter 3. The exterior angle theorem told us that any exterior angle of a triangle had to be equal to the sum of the remote interior angles, or angle 1, the measure of 1, had to be equal to measure of angle 2 plus 3. Okay, this is going to blow you away, but we have a corollary coming up now that the measure of the exterior angle 1, you know what? It's got to be bigger than 2, and it's got to be bigger than 3. I know, try and hold yourselves down, but it's true. Next, if two sides of a triangle are not congruent, then the larger angle lies opposite the longer side. So if BC is bigger than AB, well, the opposite angle, A, must be bigger than C. Okay? Now, that one sounds simple, but we do have trouble remembering it. It is fairly important, okay? If the longer side of the triangle, the opposite angle must be bigger, okay? And there is the converse is also true. If measure of angle A is bigger than C, then side BC, the opposite side, must be larger than side AB. Okay, so here's a couple for you to try on your own. Pause, get ready to go. Here come answers. Okay, moving on. By the way, I did use the sum of the angle here to find out that this was in the middle, so we know that the three angles had to add up to 180, so that was an important consideration on that second problem. All right, another new theorem. This one's really important now. Three sides of a triangle. Any two sides must be longer than the third side, okay? And think about it, if it didn't work out that way, if I had, that's not pretty. If I had one side that was this length, and one side that was this length, and the third side that was this length, these two are going to be too big to let's see. I'm sorry. I'm telling you a lie. Start over. If I have a triangle side that looks like this, a triangle side that looks like this, and the third one is bigger, notice how these two are too small to cover the length of that third side. I cannot make a triangle if any two sides don't add up to more than the third side. Okay? They can't even be equal, all right? Because two equal sides, if I had a side length that was 7 and one that was 8 and a third side that was 15, okay? Do you see how those sides would perfectly add up on top of each other, but I would not be able to make an angle so that the center point, so that the vertex would be up and off of the triangle, all right? So any two sides must be greater than the length of the third side. And we write down the three possibilities here, okay? Any two sides must be greater than the length of the remaining side. So here's how we use it. Is it possible to make triangles out of these side lengths? Answer's coming shortly. Pause. Here we go. 4, 6, and 8. Yep, any two sides are greater than the other one. But 5, 7, and 12, nope. 5 and 7 aren't long enough to cover the 12. You can't make a triangle with these three side lengths. All right. Now, when we apply this to two triangles, we're going to see a couple new theorems. All right. If two sides of a triangle are congruent to two sides of another, and the angle between them, well, the larger the angle must be opposite a longer side. Okay. If the angle is smaller, this side must be smaller than the other one. Okay. Again, the relationship between angles and opposite sides. So if x is bigger than a, angle x is bigger than angle a, then yz must be bigger than bc. Converse is also true. If YZ is bigger than BC, then angle A must be greater than angle X must be greater than angle A. All right, couple problems. Pause. Answers coming. Look good. Look good. Another example. Find the possible range. Now here we're going to use an inequality. Pause it. See if we can figure it out. Okay, so for this side, 19, since it's smaller than the 21, this angle, 2x minus 7, must be smaller than 28, right? Well, it's also got to be bigger than 0. So I know two things. I know that following this path through my algebra tells me x must be greater than 3.5, and following this path tells me x must be less than 17.5, so we have this as our final range of values for x. All right, have a good weekend. I will see you on Monday. Make sure you write a summary, and talk to y'all later.